Test, test.
Could you please close the door? My name is Pierre Benning, a co-director of the national project MIND, and I will be today your chairman for this session dedicated to the bridges. Three presenters, two remote and one here. We will immediately with Mr. Fumiya Matsushita of the University of Tokyo. Is an expert in the construction system management for innovation at the University of Tokyo. Shita, I let you the floor and I let you make your presentation. Thank you.
Okay, thank you very much. This meeting. Okay, so let me start my presentation. Yeah. So hi everyone. I'm very sorry that I cannot make a face-to-face presentation, but I'm very honored to have this opportunity, even in virtual. First of all, I would like to express my gratitude to all the members who created this conference. Oh, excuse me. First of all, can you hear my voice now? Is it okay? Hello?
Yeah, it's okay. We can hear you.
Okay. Sorry. Okay. So let me start my presentation. Yeah. I'm Fumiya Matsushita from School of Engineering, the University of Tokyo. So today I would like to give you a presentation about the development of parametric model generation method for temporary structure in the civil engineering work execution plan preparation. Before going to my presentation, although my presentation is categorized as this, discussion, but my presentation is more related to R&D or BIM. So I should be just worried about my theme is not matching with the audience interest. So yeah, that's why I apologize this point in advance. Okay. Yeah. So here's the presentation content. My presentation can be divided into five parts. First is background in item 1, 2, 3. Second is requirement definition of system in item 4 and 5. And the third is design system in item 6. And the fourth is development note type in items 7 and 8. And explain. First of all, I will explain the three words which are used in my presentation. Construction planning, product model and parametric model shown here as a term definition. Construction planning is our execution plan for construction plan objects. And one of the reasons of construction planning is for setting the target level of QCDSA means cost, safety, delivery, and the next term is the model. As you all know, the product model is object-oriented model such as IFC. A parametric model is a type of modeling parametric movement method that allows you to automatically create a model by controlling parameter of the model. I show you one parametric video shows a parametric model of an array. Number of main beam is controlled by parameter. So you can see by controlling parameter, the number of beam is like this. Okay, so let's next slide. I would like to start by talking about background and front research. As you know, optimization of the production model is core technology of T, and it is also implemented in the construction phase. And the production model is made of this. But I would like to emphasize that temporary structure. So temporary structure is required for the construction stage. For someone, in order to make a construction plan, it is necessary to the opinion of different players, including subcontractors. Especially for the we often consider revision based on the opinion of various players. Here is plans how much set according to purpose. First, clarify requirements for a construction plan that allows different players to weigh on the risk of plan. The second is that method to easily generate 3D production model in temporary structure and make it easy to define the model and reflect various opinions. In order to achieve both, I proceed this research according to the following three steps. First is review of the concept transformation process. Second step is proposal of the platform for construction planning. Third step is drop of parametric for temporary structure.
Dr. Matsushita,
This
sorry,
photo,
doc-
this photo shows an example of the situation
Doc-
of the cut and as shown in this barriers, equipment, and facilities for the set of
please, Dr. Matsushita, please,
array
can you hear me?
plan plan.
Please, Dr.
For example, this is a temporary storage area for the data, and this is the installation area, and so on. Everything is damaged by plan like this. So
Dr.
how is
Matsushita,
this
Dr.
construction plan
Matsushita,
made?
Dr.
I mean, how
Matsushita,
to make a construction plan. The construction plan can be roughly divided into two contexts. One is overview of the plan, and the other is detailed plan. The overview of the plan is planned for the following: a large-scale temporary structure design, like Ware-Armstrong, planning of construction projects, a work-yard usage plan for each subcontractor, and setting achievement targets. These results of study can be also the condition of the detailed plan. In the detailed plan, based on the overview of the plan, decide work procedure, simple temporary design,
Dr. Matsushita, can you hear me? Dr. Matsushita,
and efficient procurement plan. In the detailed plan, it is necessary to review the overview of the plan while considering the details. In such case, return to the overview of the plan and consider the revision plan. Let me show detailed plan. For example, the overview of the plan includes temporary structure design of the wall, where and strut, and consideration of the construction step. like this. Also, detailed plan includes installation plan for well and stock, and lifting plan for well and stock like this. From the perspective of the player who considers these contents, the main contractor is mainly in charge of the overview of the plan, and subcontractor and manufacturer are mainly in charge of the detailed plan. Even within the main contractor, the overview of the plan is handled by managers such
Dr.
as product
Matsushita,
managers.
can you hear
Ah,
us?
listening?
Can you hear me, Dr. Matsushita?
Yeah.
Yeah.
I can. Yeah.
I'm sorry. The sound is very awful. Could you please keep your microphone keep more close from your voice? Thank you.
Oh, sure. Okay. Is it clear now?
Yes, we can, but speak slowly and more close from your microphone. Thank you.
Okay. I'm so sorry. Okay, so now is it clear? Okay, so can I continue my presentation?
Go on, please. Thank you.
Okay. I'm so sorry. Okay, so let me restart of my presentation from this slide. So this slide shows the player which involved in the overview of the plan and detailed plan. So the main contractor is mainly in charge of the overview of the plan, and subcontractor and manufacturer are mainly in charge of the detailed plan. Even within the main contractor, the overview of the plan is handled by managers, such as project managers, and a detailed plan is handled by a site engineer. It means various players are involved in the construction planning, and if necessary, planning of revised plan, including temporary structure. That is why it is crucial to consider the construction planning platform, and it is necessary to consider modeling method that easily reflects the revision plan. The construction planning platform has a 3D design model of construction object as input and 3D model for construction management as an output. In addition, the following from A to D can be considered as requirements for the construction planning platform. To satisfy these requirements, the construction planning platform needs to have three components: construction planning system, construction simulation system, and verification and evaluation system of construction planning for QCDSE. As I have pointed out so far, temporary structure often needs revised plan to reflect various players. That is why 3D product model needs following to function as portion of construction planning system. First is a function that allows easily creation of a product model and reflect a revised plan. And second is a function that utilizes the product model with a level of detail that is required by stakeholders. Here, where and strat is taken as an example, as a temporary structure, and what kind of model is necessary as each stage is examined. At the stage of the overview of the plan, the main contractor plans the construction step. So it is sufficient to have a generic model for the HB model required for well and strat. On the other hand, the subcontractor considers lifting plan for the H-beam while considering the work procedure. For example, in this case, information on which part of the H-beam is to be lifted is required, and a maker object containing more detailed information is required. Also, when comparing generic object and maker object, it is required to make division plan for generic objects, because for the overview of the plan to reflect opinions such as subcontractor. Therefore, it is necessary to consider a parametric model for generic object. In addition, common object names among two objects is needed to associate generic object and maker object and associate with required information. Based on the discussion so far, this slide describes the development of the prototype. In addition, the prototype will be developed for DWO and well understood for cut and cover construction method. The development content is roughly divided into two parts, and the first part is development of the parametric model. The parametric model can be entered with parameters that are determined according to the construction plan formulation process. And when these values are entered, the model is automatically generated. In addition, the program has IOC output function. Here is an example of the input value. Input values are divided into two types: design value determined by overview of plan, and value determined by the detailed plan. The design values include excavation depth and length, ground height, embedding, and the values determined by the detailed plan include excavation width, well understood position, and etc. Next, regarding the development, the input information is the IFC file output from the parametric model. This development tries to make object information linkage using the common object names. By using common object names such as strat and well, we have developed a program that can associate maker objects and output that quantity requires for cost calculation. The outline of the program is shown in this figure. The program inputs a product model and common object names. The output of the program is a maker object and the construction quantity. Next, I will introduce a demonstration of the developed parametric model with a video. Only the center line of the D-ball is drawn as a figure. In this state, execute the program of parametric model. In this way, D-wall and well and strat are automatically drawn according to the input value specified in advance. It also reflects the steps of the excavation and gather construction. And the excavation width can also be changed, since it is assumed that the excavation width will be offset from the value which are decided in design stage. And also H-beam specification can be changed in this way. And the
Yeah, and the horizontal spacing of the girders can be changed in this way. Also, the vertical position, yeah, can be changed in this way. Excuse me. Yeah, here I show the yeah vertical position can be changed. Yeah, in this way. And save the model once all the parameters have been determined according to the construction plan. Next, by using common object names such as strat and where, associate maker object and output the quantity required for delivery and cost from model information. I'm sorry it's a little hard to see because I haven't created a user interface for this part. But first execute program with input value strat. As a result of execution, the maker object related to the generic object is output. Also, the quantity is shown. Yeah, around here. To sum up my presentation, I show you the presentation. I show you four parts as a summary. And as a future work, I set three parts. First is the development of parametric model for other structure, like a scaffolding. And the second is implementation of other functions of the construction planning platform. And third is consideration of a framework for system development and sharing and maintenance of this program. Yeah, thank you for your attention. That's all for my presentation. Yeah, thank you.
Thank you, Dr. Matsushita. Even if the sound was not very good at the beginning of the presentation, we are sorry for that.
Yeah, I'm so sorry. Yeah.
Do you have any question in the audience? So I have one question. I
Yes.
need to think of yours. Temporary works have to support structures, but also construction machinery, the machines which are dedicated to the construction. And how this parameter is considered in your solution?
Yeah, actually, this machinery cannot using by parametric model, and this machinery should be used as a dynamic analysis. I mean, for example, by using, for example, Unity or ROS platform, and this in this context of the construction platform, this machinery should be used construction simulation system, and this function is now under development. So yeah, that's why I cannot say the detail for this part, but yeah, this machinery should be used in this part. Yeah.
Develop some new functionalities, but what do you expect to create a specific software to sell it, or just to propose a prototype? What are the next steps for you?
Excuse me. So actually, we are under the developing of prototype to handle the machinery. So I hope I will propose that the prototype how to handle this machinery in this construction platform. Yeah.
Okay, thank you. So any questions? No? And in the chat, we don't have any questions. Please don't hesitate to use the chat for the remote attendees. So I really want to thank you, Dr. Matsushita. It was a great presentation, even if the sound was not good. Sorry. Thank you again, and we will go to the second presentation. Thank.
Yeah, thank you so much.
Goodbye.
Yeah, thank you.
Do we have the next presenters, Mr. Müller, online?
Yes, can you hear me?
Okay, good. The second presentation, it is Mr. Matthias Müller. He's a scientific employee at the Karlsruhe Institute of Technology. View. I give you the floor, Matt.
I sent a video in advance because my internet connection here is not so stable. I thought that you are going to play it, and I'm just here for answering questions afterwards.
Not yet? Where did you send your video, Matthias?
I sent it to Wei and to Wei Fang, and
Okay, it seems that we have it. Okay.
okay, good. Then I'm here for questions afterwards. Okay.
Okay, good. Not this one. Yes, we got it. Okay.
Welcome to my presentation on the topic BIM-based holistic bridge assessment. Within the scope of this work, a software prototype was developed in order to evaluate bridge variance holistically in a semi-automated way. To start off, I brought a slide from a previous project. In this project, different bridge constructions were evaluated holistically. When I say holistic evaluation, I mean that costs, environmental impacts, and macroeconomic impacts were considered over the entire life cycle. During construction and maintenance measures, there's almost always an impact on traffic, on the road over the bridge and or under the bridge. If traffic volumes are high, these can lead to long traffic jams and therefore major time loss for the general public. These time losses can be expressed in euros by using monetization approaches. Therefore, from these time losses, we get macroeconomic external costs, which are not carried by the causer, by the one who constructs or plans the bridge, but the general public, and therefore are usually not integrated into decision-making processes. It is noticeable that the external costs often exceed the actual construction costs significantly. In the project NAPRI, this analysis was done with a lot of manual effort for different bridge constructions and referring traffic situations. For example, these results come from a standard highway with 70,000 vehicles per day. Our goal is that every bridge variant can be evaluated holistically to find the best site-specific solution. However, engineers cannot be expected to carry out such a manual time-consuming evaluation, and therefore there are tools required for engineers to do this semi-automatically, and this was the motivation on the project IntecBridge, in which this software was developed. So, yeah, our goal was to develop a planning aid for the semi-automatic holistic evaluation of bridge variance with regard to lifecycle costs, ecological impacts, and external costs. And the idea is to use these BIM models as input data, transfer them via an open exchange format, for example IFC, into our evaluation software, and there calculate the impacts over the life cycle. To start off, we have to pre-balance some elements. And for bridge engineering, many components are already strongly predefined by national standards or guidelines. In Germany, for example, there are the guideline specifications from the Federal Highway Research Institute, die Bundesanstalt für Straßenwesen. Those predefinitions allow us to pre-balance components. For example, we can choose one bridge cap and balance it in terms of costs, in terms of environmental impacts, in terms of construction times, and in terms of renewal cycles. This pre-balancing has to be done for all elements which can occur on a bridge and be stored in an element database. The next point is that we want to enable the evaluation in early planning phases, because these are the ones where the greatest influenceability on the later impacts is possible. In these planning phases, the BIM models do not yet have all the objects geometrically modeled that are needed for the holistic evaluation. For example, models in primary planning phases will not have explicitly modeled shear studs. And for the corrosion protective system, it is questionable whether these will be modeled as geometric objects at all. Therefore, we worked with base, major, and macro elements. So base elements are the one which we specifically pre-balance. For example, steel beam S460, corrosion protective system, organic coating C4, and shear studs. And then we combine these base element to major elements, and all these base elements go into this major element with statistically shares. And these major elements can also be combined to macro elements. So we can have one whole bridge superstructure for a steel composite bridge consisting of 6 steel beams, of concrete slab, and so on. And all the other elements, or the corrosion protective system and the shear studs, go into this with the statistically share. And these base, major, and macro elements allow us to work in different planning phases. For example, in an early planning phase, when I'm just looking for my road, I will only use these macro elements, and when I go to more detailed planning, I can work with base elements. The advantage is when I go through these base elements, I am really precise, because I can use exactly the amount which was used in this project. And when I'm working with macro elements, I'm way faster, because I only have to assign 3 or 4 objects to my whole bridge. But the results cannot be as accurate, because all the shares of the elements go in with statistically shares and not with their project specific quantities. So now the question is, how do we get the required information from our pre-balanced database into the BIM model? And therefore a classification file containing all components can be created from the element database, in which all pre-balanced objects are stored. The classification file contains elements on different levels, for example macro elements and major elements, as well as base elements. And all these elements have to be assigned depending on how far my bridge is in the planning process. After these elements are assigned manual to the BIM model can be exported to our evaluation algorithm, and then combined with the element database, the evaluation can occur. Now we are going to see how the classification can be assigned to a bridge model. We have here our BIM model in the authoring tool Revit, and now we have to assign a classification to each BIM object, and what kind of classification we assign depends on the level of development of the bridge model. So I have my classification file, and now I can classify on different levels. For example, I select a steel beam, and now I can select, for example, one macro element, which would represent a whole bridge superstructure, which is here not the case because I have individual objects. Now I have to decide, do I use it together with corrosion protective and shear studs, or do I have my shear studs modeled separately, so I only assign one beam. Now here I don't have my shear studs modeled, so I use one major element. Then I go to the next beam and assign a different element, or I can just copy the classification to other elements. And so I work through my my complete bridge and assign each element one specific classification. Engineering companies can also assign these classifications in their BIM object libraries to not use them on each bridge project individually, but have them stored as standard attributes. Now when we go to the bridge cap, we have to decide on which level we want to assign our classification. For example, we can now use a macro element which has also statistical shares for guardrail and for railing, which is useful here because this is needed for the later evaluation, but has not been modeled yet here in this planning phase. So we assign now this macro element. We already consider the railing in our evaluation, but we do not have to have it modeled in this early planning phase. After the classification is done, this is just stored in the element itself as two attributes. We have one attribute which represents the description, which is for the user to see what it means, and we have this code, which is the classification code and used when imported into the software that the algorithm can see what element was used. So now we just have to export it as an IFC file. To transfer the data into our calculation algorithm, we worked with open and closed BIM approaches, but in the end we went with IFC to be software independent. So now I'm just going to show you how this can look in a prototype. So we start with importing our IFC file, and now when we want to transfer, now this IFC file is read and we want to transfer the data, it gets mapped. So each IFC object gets mapped to a database object, and there are some specific information we need which cannot be derived from the BIM model. For example, the bridge area, bridge type and construction type we have to choose manually. And now we get all the elements which were recognized by the software, and here each row represents one element. If it has only one dot, it means that it's a base element. If it's 3 dots, it's a major element. If it's 6 dots, it's a macro element. And here now we have, for each element, we have a short description, what it means. We have the quantity, we have the reference unit, but we can also see the information which lays behind each element. So therefore we just select one element, we click on this info button, and now we see the data which is in the database for this element. So we see a short description of the element, we see the reference unit, the costs, the renewal cycles, the global warming potential, and so on. And we can see, because here we have a major element, what are the base elements which are with their statistical shares into this element. This is just basic how the import works, and now we can of course adjust our project. For example, if something wasn't transferred correctly, we can change the quantities, we can delete elements, we can change the composition of elements, or we can even add new elements in the software which were not modeled in the BIM model. So next, traffic is the most important input variable for the calculation of the external costs, but this cannot be derived from the BIM model. In order to be able to calculate the time losses and therefore the external costs, many parameters such as the gradient, the annual daily traffic, the heavy load share, the speed limits, the detour options, and the distribution of the traffic over the day and the week must be defined. To input the traffic data into the calculation algorithm, there are different possibilities. One possibility is to just choose a standard scenario where all the other parameters are already defined, or you can go more into detail and define each parameter for itself. For example, you can adjust the speed limit, you can adjust the gradient, you can adjust the distribution over day and week. This would be done in a more specific planning phase, and the other standard scenarios can be done to do a fast modeling in early planning phases. The next important parameters for the calculation of the macroeconomic costs are the construction time and the traffic routing for the construction measures. The construction time for each measure comes from the pre-balanced elements together with the quantities from the BIM model, and the traffic routing during these construction measures can be chosen in the software. For each traffic routing, there are in the software behind specific capacities for the lane and the ongoing lane to calculate the traffic jams and time losses during these construction measures. To calculate impacts over the whole life cycle, we need information when which part has to be replaced. In previous videos, projects, different maintenance strategy with replacement cycles in Germany were elaborated. In short, there are 3 different strategies. The first one is the preventive strategy, which has to go to keep the bridge in top condition over the whole life cycle and therefore do a lot of measures. The second one is the condition-based strategy, which bundles measures over time, and the third one is called strategic aging, which is just a nice word for doing nothing for 50 years and then restoring everything. And all these different maintenance strategies have different measures over the life cycles. How do we get our replacement cycles? There were different approaches we worked on in the past. One was to evaluate literature values and to work with engineering companies, and another one is to evaluate databases. For example, in Germany we have this bridge database ZIP Bauwerke, and in this database all measures over the life cycle of a bridge for all bridges in Germany has to be stored. Therefore we can do a statistic evaluation to see how long the service life of one specific bridge component is statistically. In the software this was implemented with follow-up elements. So we have our base element, for example one corrosion protective system, and these base elements now have maintenance and repair elements which always occur after a specific cycle. And then we have after the service life of the base element is reached, we have our selective dismantling element and we have our renewal element, and after this renewal element all the other maintenance and repair cycles start again. Then after the lifespan of the bridge is reached, we have our dismantling element, and for the selective dismantling and for the dismantling we also have end of life and module D elements which are required for LCA. Now again I'm just going to show you how this was implemented in our software. So we have our elements, we see our base elements which are now dark blue, and our follow-up elements for each element which now have a specific new column, and this new column is the Nutzungsdauer or renewal cycle. First of all we have to choose our traffic routing for each measurement, and then we can see our renewal cycle, and there this renewal cycle is now strategy dependent. For example, we have our condition-based strategy where we have a lot of measures done in the year 35 or 70, and now we can also choose another strategy, for example preventive strategy. This strategy has now other renewal cycles and other service lives, and therefore more measures. Or we can use our strategic aging strategy where we only have a lot of measures in the year 50 and the rest only the necessary measures. So each element has different service lives stored in database depending on the strategy, and not all elements are used for each strategy. So when you choose a strategy, these elements get from the database into the project. Now we have all the required data together. We have our element database which gives us the pre-balanced data. We have our BIM software where we get the project specific quantities. Then we have the manual adjustments for the traffic and strategy, and we have our pre-balanced traffic data, and now all this data is combined together to allow us to evaluate the bridge holistically. Okay, now we go through the evaluation. And on the dashboard we see the most important results, for example the costs, then the cost of the life cycle, the macroeconomic costs and the global warming potential of the bridge. Then we can see all these costs separated through the different elements, and we can see our most important boundary conditions on the left, because these are important because they define the results, like the used strategy or the bridge service life. Now we can go through the costs. There we have different evaluation options over time, over elements, or we have a small table with the most important information. Or if you want to go more into detail, you can see, okay, why are my costs so high? You can click for each element. You can go for all the superstructure elements, or you go for all the beams, and then you can go lower to the follow-up elements and see why the costs on this element are so high. Then we also have the same for the ecological impacts. There we have for each impact category our own dashboard. So for example for global warming potential, you can see which element causes which global warming potential over the life cycle. And for the global warming potential you can always see in detail for all impact categories. Similar evaluation options exist for the external costs. You can see the external costs over the life cycle, or you can see how many costs come out of the time losses and how many costs come out of the operational costs. And if you want to go more into detail, you can see the external costs for each year. And now it's getting interesting because we can just compare different bridge objects together. For example, we can go back to our bridge, and we can now change the quantities, or we can compare different corrosion protective systems. We can go through the construction phase and decide on another traffic routing, or we can even change the strategy, and then we can do another evaluation and can see, okay, maybe for this bridge this corrosion protective system would have been better, or for this bridge maybe we should go with this strategy or with this traffic routing. This is the prototype we have right now, which works for bridges, and now we are working on to extend these holistic evaluation. So right now we are working on a project to combine the road and bridge evaluation. Then we are working on to connect to open databases. So for example, in Germany we have the ÖkobauDat, where we now already use some values, but the problem is that for bridges not very much data is available in ÖkobauDat. And then we are extending our holistic evaluation to other criteria. For example, when we are looking for roads, it's also important how close are we to specific nature reserves, or how good is the protection against, or are we crossing any flood protection areas, for example. If you're interested in further information, we have some videos on YouTube where you can see the whole workflow explained a bit more in detail. Unfortunately, these videos are only available in German until now. Thank you very much for having me, and I am here for any further questions.
Thank you, Matthias, for this brilliant presentation. Here in the audience.
Hello, my name is Paolo from Italy. My question is about the new development of IFC for bridges, I mean the new standards. How do you want to implement it in your very beautiful system? Thank you.
Well, we are looking forward to the development of the new IFC standard. Well, for us it's more important when it gets into the vendor software, for example in the authoring tools. How we want to use it? Well, right now we have the problem that, as you said, we have no IFC for bridges. Therefore, we are working mostly with IFC for transfer view. And for some bridges, there are difficulties with quantity, because when we have a bridge which has a curve, of course, we have no alignment, and therefore quantities get not transferred so good. But when we have this IFC bridge or IFC 4.3 implemented in the authoring tools, we are looking to get a better IFC export, and therefore only have a better system to work with. But it will be implemented, of course. We are just waiting for it to be available.
Okay, thank you, Matthias. Other questions? I have a question. You talked about the cycle analysis. Do you think we could evaluate the carbon impact of different alternatives with your technology?
You mean if we could compare different alternatives with this tool?
Yeah.
Yeah, that's the. Yeah, so the climate warm potential is, of course, one of the aspects. We want to look at it holistically. So we want to have costs, ecological impacts, or carbon footprint, however you want to call it, and these external costs. But yes, of course, our point is that you use this software to compare two different variants and then decide, okay, this bridge has higher costs, but this bridge has lower carbon, and therefore you have something for decision makers to get an informed decision on the chosen option. If I understood the question correctly.
Okay, we don't have any questions in the chat. I look at it. Okay, done. Okay, I thank you very much, Matthias. It was very interesting, very brilliant, and I hope that we will get your video.
Okay, good. Thank you very much.
Yes, and look at your video on the. Very much, Matthias. Goodbye.
Okay, goodbye.
have a third session from Bernardel of Padova. Bridges. Interesting. Thank you.
Okay. Okay. No worries. Okay. Fine. So repeat just a little bit if there is someone online. It's a joint work project developed at the University of Padua and in collaboration with other two colleagues of mine, which are Paolo Borin and Alberto Longhin. Methodology that we propose is is developed with an integration among these all programming languages, scripting, IFC 4.3 semantic, and online sharing application. The combination of these three different tools is able to is aimed to enable different model uses of existing bridges, which represent strategic asset in the national communication infrastructure system. Doesn't go. Okay, probably it takes. It's not going. Okay, so let's do like that. Okay, so okay, probably you can see it. Okay, fine. The work is based on two different approaches, which are aims to standardize the approach to the maintenance of bridges. The first one is the Italian guidelines, which have been published in May 2020, and so the aim of the guidelines is to have an harmonized method among all the national territory in order to have the same approach to the bridge maintenance and to have also the same management of bridges. And the other approach is the Yes, IFC schema, and of these schemas we use, of course, the methodologies and the taxonomy and the relations between objects. So although we know not yet completely supported by software, but so knowing the development process of the IFC 4.3, that it can ensure the information exchange with public administration, and also because in Italy it's mandatory the use of open formats for the project related to public assets. So with a link between these two approaches and these two standards, what we want to propose, it's a massive bridge modeling, so in order to assure the maintenance of bridges. So for those who don't know how the Italian guidelines work, this is procedures, guidelines developed for ordinary bridges, and it is based on 5 levels of analysis. The first 3 levels, as you can see, are based on all bridges, so a large amount of bridges, and it is an evaluation on a larger scale of the territory. And the last 3 levels goes more in depth on the evaluation of the bridges, and they are related on a small number of bridges, but they goes more in depth in order to understand how the how to manage, and so also to define the strategies in order to do the maintenance of the bridges. Okay, so to summarize what happens, in the guidelines in this multi-level approach, we have that for the first level, the 0 and 1, you have a low level of detail of the modeling, but a high number of bridges. On the opposite side, when the level goes to the 4 and 5, you have so the number of bridges goes down. We have less bridges, but the level of the survey and of the analysis goes higher. Okay, so what we do in our work, focus on the information that we need and that we have to give into the first 2 levels of the So the first, the level 0, is devoting to gathering the available data on the individual bridges and what they want. So what the guidelines want from this level 0 is to have a kind of the information related to the bridge itself, how many bridges we have, the number, the ID, and all of this first information related to bridges. And then the level 1, which foresees specific site inspection for verifying the current state of degradation and the possible presence of structural and non-structural components affected by significant defects. What we did was to use this the information obtained from this 2 first level in order to produce this massive modeling. Okay. On the opposite side, what we take from the IS schema actually was the semantic and the dictionary, so the use of the element and the organization, and also the how to manage the information and how to create the relationship between elements and between the special structure. Of course, what the alignment, and so the object positioning and the sweeping of the element along the path, and then the organization of the spatial structure, and then of course, as I mentioned before, the taxonomy of the element and the geometry representation. On the possibility to give properties to the model and to attach properties was one of the things that is implemented. Okay. In order to do this proof of concept of our methodology, 2 types of bridges were implemented, and the methodology were tested into 2 types of methodology. So in order to the widespread existing bridge type, most common ordinary bridges that are we have in Italy. So these are the steel concrete composite eye girder bridge and the precast presets the concrete box girder bridge. So the ability of the massive modeling process is connected to all factors. At first we have of course the analysis of the geometries and their relations in an existing bridge. So what we did was the study, the connection of the properties and relationships between the shapes and between the elements into the bridges. And then of course extend and to set a hierarchical system related to the spatial and functional structure. Then what other factors and of course opportunities that we can highlight is that visual programming platforms implements so the rules and the geometric relations. So we have set the simulation and the information exchange with other systems, and then defined a vast catalog of models by modifying the parameters and to set change parameter, and find the level of detail of the formal definition of the structure for saving time. What we also, another factors is the approach and the approaches of the BIM modeling methodology and software, and so that are able to describe the assets. This, all of these factors, allows us, and so they helps us to connect the methodology that we are proposing, and so the results of these methodologies, the bridge management system that are used by the local and the owners of the bridge itself. Thoughts actually to combine the data of the survey with the data model and the structure of the data model itself in order to saving time, cost, and all the other resources. So the other things was actually use of the use of scripting allows us to show that the methodology is not related to a specific software vendors. So actually, with the use of scripting, and so it works, and how it is, how the use of the VPL, so we can clearly and definitely specify the relations, the geometry, and so all these choice of the model itself are made by the and so we can actually be apart from the specific software and just define all the structure of the BIM model that we want. It's in the slide. So the use of the scripting is allows us to show the proof of concept. We are not developing software. We are just showing a methodology that can be implemented by the actors, and that can adapt also to the platform that each owner has in its own process or in its workflow. The VUP that we use was of course Grasshopper, as you can see, create parameter models and also change the configuration quickly of the geometries related to the bridge structures, changing the different parameters and by the inspections. In order to the relationship, the element, and all the semantic assignment of the data schema, what we used was also an UML representation. This has two different scopes, and these are at first to define clearly the semantic, the relations of the elements, but also we use the UML diagram in order to dialogue and to demonstrate our methodology and to show clearly in a format that is not the VPL or the scripting, but is that we use in order to have a presentation that can be understandable by all the users involved in the process. So here you can see the process summarized. So and the software that we used, so in the different tools. So at first we are here, and we have all the collected information from inspection. So at first we have the information from the 2 levels of the guidelines and all the information collected by this. Then we have the second part, which is the geometry scripting in Grasshopper, and here we have the first output of our method, which is the geometric model. Then we have the mapping of the IFC into the ISC classes and using Geometry Gym. And then this model are uploaded into a platform, an online platform, in order to have the online creation and modification itself. And then when mapping of the properties into pset, what we have actually is the combination of the classic mapped into IFC plus the properties and the pset attached to them. We have the IFC model, and I will show you and the use of augmented reality in order to complete all the process. So here, I don't know, okay, so we had an animation, but in order to, so as we said, so the use of the UML, as you can see, it's not just, so it wasn't just used at the beginning in order to develop the process, but it is used also to show the methodology. Our process starts from the definition of the site and the morphology of the territory where the bridge is. And then what we have actually is the definition of an alignment. Probably if I do like that, okay. I do the animation manually. So we have the definition of the alignment starting from an external data input. And what we can do actually is defining the starting point and the ending point and the curve of the alignment itself. From the alignment, what we had then is the application of the spatial structure of the bridge. So substructure, the foundation, bridge, but also to then have the containment of the element that we have to during the inspection phase. Here another example. So I want to highlight that all the procedure that we use to create the geometry model so they take the information from the inspection, but as you can see from the UML model, so it is important to clearly define in the creation of the geometry that the creation of the elements here, it's related to how they are placed into the model itself. Okay, so here we had another animation, but it was something I tried to do, so, but no, it doesn't work. Okay, add the okay, nothing worked. So it was something to show you that changing some parameters in the Grasshopper files was just changing. Okay, so it was from these 4 different point of views of views and the 2 front and the free frontal view of Rhino, what you can see is that changing the information, you can change the curvature of the bridge itself, you can change the number of spans, the number of the foundation, how many, so the number of piers, so the typology of the piers, if you have a unique pier cap, or if you have double, if you have one or more columns. But for us, what is important is to manage all of this information directly by just changing some parameters. Then, what we have done is using Geometry Gym to map into the IFC 4.3 schema the information of the the object, and then to map also the properties and to attach the information that was used in order to create the model also as properties of the IFC file. Okay. So the online interface that we provide, again, as such as a proof of concept, to simulate the interface between the WPL script environment and then the user. So again, knowledge and different skills of the people to the process. So this was to highlight that the user at the end is the person that has to change the parameters, set all the conditions, and then if it is needed, imported also external reference. And of course, this online interface can be the BMS of the client itself. Okay. So here you can see that some of the parameters, okay, can be changed also in the online platform. You can visualize the bridge itself, and you can change then some parameters defining different types of changing the same parameters that was set to do the model into grasshoppers. Some of the parameters can be modified and can be set also into Shapediver. Uploading also external reference, for example, as profile of the pier columns or of the pier cap, and also of the girder of the deck itself. And again, so just to show that this is possible, that the final, the inspectors that doing its own activities can modify this information and these parameters in order to have this quick model of the bridge. Okay. At the end, the other test that we have done was to set and to upload the model itself into an AR device, so a platform and then device, in order to show the opportunity to use AR devices during the inspection phases. Of course, now we are kind of testing all of this information with the inspectors itself in order to understand how it is, if it is possible, if it is useful, in which kind of situation it is possible and useful to have an AR development. To conclude, this kind of the summarize and the conclusion of the process, actually, this is a method that how a process, a methodologies that can be used in order to combine the information of a national guideline standard of inspection, in this case the Italian one, how to combine with a process a correct geometry, relations and continuity between the elements, and then how to have a different ways to change the parameter, and finally the use of the AR as other development, and in order to combine methods with the bridge management system. Thank you for all the attention, and sorry for this kind of.
Thank you very much, Raffaele. It was very exciting. I have one question. Did you evaluate the
Sorry, I missed a word.
did you evaluate the stage of bridges that you could Italy, of course?
Yeah, actually it's around 70 and 80%, because in Italy we have these two types of bridges, box and eye girder bridge, and then we have another typology which is, for example, the masonry bridge, which are widespread, of course, in Italy, but actually we choose these two types, the widespread.
So 70%.
Yeah, more or less.
That's good. That's good. I'm not sure that in France we have this. Edouard? we have this kind of approach in France. Questions?
First of all, to say that Pierre is one of the further I see for bridge, so. Okay. Now, according to the discussion we have yesterday, I think there is one thing. I understood that it's a proof of concept. Did you an idea, because in IC 4.3 you have not all of the property set. We know that from the very beginning, and we have populated with Edouard the BSDD with much more information. It's already available in the BSDD, and ACA is able now to have a complete view about IC 4.3, including the alignment. I think that Geometry Gym is also able to do that. But my point is more or less what we said yesterday about the question is, the question is, are you imagine that the question of object type could be useful if we are going in detail of the properties to be applied for that? Because I think what it was says that if we want to align all of the properties to each element could be very it's a huge effort. But to go to catalog of object already assigned or with the properties already assigned could be useful. So it's my question that first of all, are you aware that there is much more properties as available in the BSDD regarding bridge, first of all? And then the question is, in your approach, that is the object type could be not useful to have a more industrial approach of that, to have a systematic, massively approach of the asset. This is my question.
Yeah, thank you for the question.
In any case, and the alignment-based reference view works for that.
Thank you for this, and thank you also for the questions. So for the first part, BSDD, yes, we are aware of it, but we didn't implement it in this part. And the use of the object type, actually, it was the focus. From the Italian discussion that we have in Building Smart Italy and others, so also the discussion with other companies, the possibility to use the object type for us is fundamental to attach the properties. In fact, so what the guidelines highlight is that some properties cannot be attached to the elements, but they have to be attached, for example, to the special structures, for example, the spans. There is a lot of information for the maintenance that are related to that. And so this, of course, was really useful to us, the use of the object type, and actually we implement it.
Good. Other questions? I have to look at the chat. Sorry, I have to manage a lot of things. No, we don't have any questions in the chat. So I have to thank you, Rachel. It was very interesting. And thank you to have participated to these 3 sessions on bridges. And just a reminder, we have to have a lunch seated. So take a box and take a table and do not move while you are eating. Thank you, and have a good day. We have a beautiful building, but we have also a beautiful town. So if you have time, go and see outside what is it, the Lion City. Okay, so thank you, and have a good time. Bye.